All right. Good morning, everybody. So just a quick announcement for this week. So we are not having the in-class assignment on Friday, okay? Because we already had last Friday. So we are going to have lecture today and on Friday. So let's start the lecture for today. So let me start sharing my screen with you. Okay, so now I would like to start a new part of our course, probably the final part. And we are going to take a look at inorganic reaction mechanisms and catalysis. Okay. So inorganic reactions are very, very important, and they are all over the place in most of the catalysis mechanisms and reactions. And as we can see here, we have several examples of inorganic compounds that act as catalysts in the most wide variety of organic reactions. So as we can see here, we have examples for the hydrogenation using the Wilkinson's catalyst, the Monsanto acetic acid synthesis, and also, for example, here the Sonogashira coupling. And as you can see here, the catalysts are not that kind of complicated compounds. They are usually composed by late transition metals or the heavy transition metals. For example, here we have a rhodium catalyst here as well, and here a palladium catalyst. And those are the most common elements that form catalysts. Okay, let's start talking about chemical reactions. So when we see a net chemical reaction, it does not tell anything about the mechanism or mechanisms involved in the formation of the product. And here I'm showing you two different examples. The first one coming from organic chemistry. So if you remember, this is a Friedel-Crafts acylation. And we have here an acyl chloride and benzene, and this reaction needs aluminum chloride as a catalyst, and then you couple this acetyl group to the benzene. And the second example is the acetic acid synthesis by Monsanto. And here we force carbon monoxide to get in the ethanol structure using a rhodium catalyst. And this kind of reaction is the one that we are going to focus more in this course, okay? But looking at the chemical reactions, the net reaction doesn't tell you anything about how the reaction proceeds or what's the mechanism for the formation of the product. Okay, so I would like to start talking about the kinetics and thermodynamics aspects for the reactions. Okay, chemical reactions may or may not happen spontaneously with slow or fast kinetics. Thus, it is essential to differentiate between kinetics and thermodynamically favored reactions. They are two different things. Let's start with the kinetic aspect of a reaction. The kinetic aspect of a reaction is related to its activation energy, or the energetic barrier that needs to be overcome to get to the top of the mountain, okay? Low activation energy reflects in fast reactions, while high ones reflect in slow reactions. So just think about if you need to go to the top of a mountain, if the elevation is small, it's pretty easy to go over the top and then to the other side. So small activation energy means fast reactions. And high activation energies, the energy barrier is high, so it will take longer to get to the top of the mountain and then to the other side. That reflects in slow reactions. And here we have two terms that are correlated with the kinetics of a reaction. First one is labile. So that means metal complexes that have fast kinetics, and inert metal complexes that have slow kinetics. All right, let's see here two examples for two different reactions. Let's start with the first one on your left side. This is a diagram, energy against reaction progress. So we have here our starting point, the reagents, the energy of the reagents. So the reaction needs to be activated all the way to the top, and then after that it will go by itself and finishing here at the end. And this is the energy of the products. And for this first one, the activation energy is the energy between the start and the top. So that's the activation energy. And the second reaction proceeds in the same way, starting from here, going to the top and then down. And for this case, the activation energy is the energy between this point over here and the top of the reaction coordinate. So my question for you is, which reaction has a fast kinetics or is fast, and which one is slow? So let's think a little bit about that. Okay, this first one has high activation energy, therefore is slow, while the second one has a small or low activation energy, therefore is a fast reaction. The problem here is to label fast and slow. Is there any quantitative limit for a reaction to be fast or to be slow? So the answer for that is yes, there is. And here we are going to talk about reaction half-life. The reaction half-life is the time necessary to decrease the concentration of the reagents by 50%. And according to Taub, if the reaction half-life is smaller or equals to 1 minute, the complex is labile. So that's the time limit for a reaction or a compound to be labeled as labile or inert. 1 minute half-life. Okay, so now let's move on to the thermodynamic part of reactions. The thermodynamic aspect of a reaction is related to the free energy variation, or delta G. Remember, if delta G is negative, the reaction is spontaneous, while delta G positive means a non-spontaneous reaction. And here we can label compounds as stable, or compounds that have low energy, and unstable, which means compounds that have high energy. There is a correlation between delta G, delta H, and delta S, and that's described here. Delta G is equals to delta H minus T times delta S. Delta G is the free energy, delta H is the enthalpy change, and delta S is the entropy change, and T is the temperature in Kelvin. So if delta G is negative, the reaction is spontaneous, and if delta G is positive, the reaction is non-spontaneous. So usually when a reaction is exothermic and results in increased entropy, this reaction is spontaneous. Okay. So let's take a look here at two different reactions. The first one, the energy of the products is lower than the energy of the reagents, and in the second case is the opposite. The energy of the products is higher than the energy of the reagents. What does that mean? So it means that in the first case, the reaction is in a direction of forming products with lower energy or more stable, and in the second case, forming products that have high energy, therefore are less stable than the initial state. First case, here we have an exothermic reaction, and in the second case we have an endothermic reaction. Which reaction is spontaneous and which one is non-spontaneous in this case? All right, so the first one should be spontaneous, and the second one should be non-spontaneous. Okay, so one thing that I want to make it clear here is that if a reaction is spontaneous, doesn't mean it will occur. It means it has high probability to occur. And the same thing for non-spontaneous. It doesn't mean it will not occur. It means it has low probability to occur. And the same thing with a fast and slow reaction. It doesn't mean it occurs, okay? We have to have a compromise between the kinetics and the thermodynamic aspects of the reaction for it to occur. Okay, so let me show you some energy diagrams here. So let's focus first on the top row over here. So diagram A shows a reaction where the energy of the products is lower than the energy of the reagents. Therefore, this is an exothermic reaction. and should be spontaneous. However, the activation energy is high, so that means this reaction has a slow kinetics, okay? So energetically or thermodynamically speaking, it should occur, but the kinetics is slow, okay? Therefore, this is a spontaneous and slow reaction. Let's move on all the way to the diagram C. In this case, the energy of the products is higher than the energy of the reagents. Therefore, this is a non-spontaneous reaction. However, the energy of activation is pretty small, so that should be a fast reaction. Okay, so therefore, in the case C, we have a non-spontaneous and fast reaction. Now let's take a look at the diagram shown in B. This diagram is slightly different. So we have the starting point here, activation energy quite high, so that should be a slow reaction. However, there is a little valley here, and then the reaction goes again and then goes all the way down. So the presence of this kind of valley or depression here means that the reaction forms first an intermediate state and then goes to the second step and proceeds all the way to the end. Okay, so this reaction here needs to form an intermediate, is spontaneous and slow. Okay, now I would like to talk about kinetic product and thermodynamic product. What's the difference between them? So let's take a look at the energy diagram here at the bottom of the slide. So we have our starting point here, and this reaction can go one way and forms the product B, or another way represented here by the dashed line and forms the product A. So my question for you is, which product, A or B, is the faster to achieve? So the faster or the fastest product here to be formed is the one with the lower or the lowest activation energy. Therefore, forming the product B is the fastest. However, is B the most stable one? The answer for that is no. The most stable product is A. Okay, so here we have one thing called kinetic product, which is the one that's fastest, which is the one fastest to be formed, which is B, and thermodynamic product, which is the one with the lowest energy, which is A. And that's the difference between thermodynamic and kinetic product, okay? The kinetic product is the one that has lower activation energy, therefore is the fastest one to be formed. And the thermodynamic product is the one that has the lowest energy, or is the more stable. Okay, so for this reaction, if we run it for a short period of time, we are going to form a lot of B and a little bit of A. But if we leave the reaction for a long time or longer times, more of the product A is going to be formed and less of B. Okay, so the reaction will try to form the most stable product, which is A in this case. Okay, guys. For the inorganic chemistry, the most important reaction is the substitution kind. Okay, so just remember here, substitution reaction means that one of the atoms, or in this case, one of the ligands, is going to be replaced and get kicked out from the coordination sphere. So general example here, metal coordinated to 6L ligands is going to react with a Y ligand. So Y ligand is going to get in the coordination sphere and one L ligand is going to be kicked out. So that's going to be the net chemical equation or net reaction. This reaction can proceed in two different ways. Without the presence of an intermediate, which is represented by the first energy diagram. Okay, just one hump here, and the reaction goes all the way to the end, or in the presence or with the presence of an intermediate state, as represented by the second energy diagram here. Okay? So reaction starts, stops to form an intermediate, and then goes to the second step. Usually, in most of the cases for inorganic reactions, there is at least one intermediate state present. Okay, so that's the most common kind in inorganic chemistry. Okay, there are three different mechanisms for substitution reactions in octahedral complexes. The first one is called dissociative mechanism. Second one, associative mechanism. And the third one is called interchange mechanism. Sorry. The symbols are Da and I respectively. So let's start discussing the D mechanism. So dissociative mechanism means that the first step consists of the dissociation of the complex. So as you can see here, one ligand is kicked out from the coordination sphere. So ML6 is going to form an intermediate complex ML5. And the geometry is going to go from octahedral to square pyramid. Okay, so this is very important. So we are going to change the geometry. So we are going to change how the ligands interact with the orbitals of the metal, and that will have an influence in the energy that we are going to see on Friday. And the second step is the addition of the Y ligand to the coordination sphere, and that forms Ml5Y and restores the octahedral geometry. All right, so first step, dissociation. Second step, insertion of Y and forming the final compound. The characteristics for this mechanism. First one, formation of a 5-coordinate intermediate, and the first step, or the dissociation step, is the most important. And third characteristic, there is the formation of a long-lived intermediate state. Okay, the second kind, or the second type of mechanism, is called associative mechanism and is represented by A. And in this case, the first step is the association between ML6 and Y. Sorry, I'm missing here a Y. Okay, so association between ML6 and Y, and that's going to form this intermediate complex ML6Y. So as you can see here, you start from coordination number 6 and move to coordination number 7. So you are expanding the coordination number. So this step here will be really, really important in the future. And the second step is the losing of one of the L ligands, and that's going to form the final complex ML5Y and one L ligand that's free. And that restores the octahedral geometry. Characteristics of this mechanism. First one, formation of a 7-coordinate intermediate, as you can see here. The association step is the most important, okay? So the formation of the 7-coordinate species is the most important. And third one, there is also a long-lived intermediate state. And now let's move on to the third mechanism, and this is the interchange mechanism represented by the letter I. So the interchange mechanism is different, of course, from the other two that I showed you. And in this kind of mechanism, there is the formation of an intermediate state where the leaving and incoming ligands are partially bonded to the metal. Okay, so this mechanism is similar to SN2 reactions, where there is the formation of a compound here where the incoming ligand and the leaving ligand are partially bonded to the metal. As you can see here, I represented that by this dashed bond here, okay? So partial bond between Y and M and L. And then second step, the ligand leaves the coordination sphere and we restore the octahedral geometry. In this mechanism, we have a short-lived intermediate state and we have two options. One of them is called associative interchange, IA, or dissociative interchange, ID. So now let's talk about associative interchange and dissociative interchange. Okay, so starting with associative interchange, IA, in this mechanism, the most important step is the bonding between incoming ligand and the metal, or step number 1. So I'm showing you here again. So for this mechanism, this is the most important step. And a characteristic of this kind of reaction is that this mechanism is heavily dependent on the concentration and nature of the incoming group. Therefore, different ligands will result in different kinetics in substitution reactions that undergo the associative interchange mechanism. In other words, the kinetics of IA reactions is going to change depending on the ligand that you are using, or depending on the Y group that you are using. And that's a clue for us to decide between associative interchange or dissociative interchange. Associative interchange mechanism depends on the concentration of Y and the nature of Y. If we change the ligand, it will change the kinetics. All right, so now let's talk about dissociative interchange, ID. For this mechanism, the most important step is the release of the leaving ligand, or second step. So just think about the name, dissociative or dissociation. So it means the most important step must be the release or the dissociation of the intermediate. So I'm showing you again here the second step. All right. So we have ML6Y and the release of one of the L ligands or the dissociation step to form ML5Y is the most important step. And this kind of mechanism is not dependent on the concentration and nature of the incoming group. Therefore, the kinetics is not dependent on the nature of the ligands in substitution reactions that undergo the dissociative interchange mechanism. So, if we change the ligand and the kinetics does not change or change in a small scale. So that means this reaction undergoes the ID mechanism. Okay. So to decide between IA and ID, we have to have a set of different ligands and measure the kinetics of the reaction. If the kinetics changes with the ligand, that means is an associative mechanism. If does not, it means it's a dissociative interchange mechanism. Okay, so I think this is a good point to stop. So here we started introducing to you a little bit about inorganic reactions mechanisms. So I told you about the difference between kinetics and thermodynamics when talking about reactions. Remember, slow and fast reactions are correlated with the activation energy of the system, and we can label compounds as labile, which means fast reactions, and inert, slow reactions. Looking for the thermodynamics, what is important for us is the free energy. So negative free energy means spontaneous reaction, and positive free energy means non-spontaneous reactions. And we can label compounds as stable, which means low energy, and unstable, high energy. We also saw some energy diagrams and how to decide if a reaction is fast or slow, spontaneous or non-spontaneous, when there is the formation of an intermediate, difference between kinetic and thermodynamic product. And I started talking with you about some different substitution mechanisms in inorganic chemistry. So we saw 3 different mechanisms: dissociative, where there is dissociation of the complex to form a 5-coordinate intermediate; associative mechanism, where there is association of the incoming ligand forming a 7-coordinate compound. In both cases, we have a long-lived intermediate state. And then the third kind of mechanism called interchange, where there is a similarity with SN2 reactions from organic chemistry, and we have a short-lived intermediate. Interchange mechanism can happen in 2 different ways: associative and dissociative. Associative mechanism, the association step or the first step is the most important, and the kinetics is dependent on the nature and concentration of the incoming ligand. Dissociative, the dissociation step is the most important, which is the second step, and this kind of reaction or this kind of mechanism does not depend on the concentration and the nature of the incoming ligand. Okay, so let's stop here, and then on Friday we will talk about the factors that influence each of these mechanisms. Okay, so if you have any questions, just let me know. I will see you on Friday.